Hello, my name is Arkady Zaslavsky. I work for CSRO Australia, and I'll be introducing a project that we are involved with. It's a European Horizon 2020 project bIoTope, building IT open innovation ecosystem. And our team is responsible for developing a platform called Context as a Service. The video clip, which you will see with the help of our PhD students Ali Hassani and Alexey Medvedev, will be showing how our CoaaS platform enables smart mobility use case.
Meet Claudia. She is a happy owner of an electric BMW car. As part of her duties, she has to visit lots of different places around the city, and she meets a number of common problems. These problems include finding a proper car park with a charging station, avoiding roads with roadworks, accidents and other factors which cause delays. And on top of all that, when she gets to a car, the temperature inside is usually far from being perfect, which is very disappointing. BMW cares about experience of their customers, so they're looking for a solution to provide preconditioning, real-time smart routing, and car park suggestion services. In order to provide the best possible suggestion, it's vital to be able to retrieve the contextual information about the driver, car parks, charging stations, roads, and other involved entities in near real time. There are plenty of challenges that need to be addressed to properly fulfill these tasks. These challenges include service discovery, data retrieval, data fusion, processing and reasoning. Moreover, we need to consider performance and scalability problems. Even for an expert team of software developers, it is an expensive and complex task to design and manage such a system. To ease the development of systems which need real-time context horizontally disseminated across data silos and domains, we have designed and developed the Context as a Service platform, which we will refer to as CoaaS. The CoaaS platform allows developer to issue queries in specially designed language called CDQL. We will show some of the capabilities of the CDQL language and CoaaS platform later in this video. Let's get back to Claudia. She has planned a meeting in her customer's office. She added the time and location of the meeting to her Google Calendar. Besides, she has an application installed in her smartphone that sends some contextual information to the CoaaS platform. As Claudia starts walking towards the car, the smartphone app sends her location to the server in a form of periodic messages which are processed by CoaaS event processing framework. Based on the information about the distance decrease between Claudia and her car and meeting planned, CoaaS reasons that the car is likely to be used. This triggers sending a notification to BMW Connected Drive, which starts the preconditioning process. By the time Claudia reaches the car, the temperature inside the cabin exactly meets her preferences. What was needed to be done for this magic to happen? The BMW backend registered a push-based query in CoaaS. A push-based query is a subscription which is triggered when a particular situation happens. In our case, the query contains a preconditioning function that detects that adjusting the temperature inside the car might be needed. This is done by monitoring Claudia's location together with car's location and cabin temperature. When Claudia starts the car, the Connected Drive requests information about suitable car parks near the destination. CoaaS discovers matching parking facilities and retrieves real-time information about capacity and additional related contextual information. Using this information, CoaaS identifies the best available car parks and sends a list to the Connected Drive. Based on the suggested list, Connected Drive backend plans a route to the destination car park. As a first step, the initial routes are being built and sent to CoaaS as a part of a pull-based query. A pull-based query requests information only once. In our case, the information regarding surrounding context of chosen routes is requested. This can include public events, road accidents, and other factors. Having this information, the BMW Connected Drive builds a final route and sends it to Claudia's car. Further, it also sends the route to CoaaS, which triggers a push-based query. The push-based query subscribes for situation changes on the route. If something happens on the way while Claudia is driving, the Connected Drive will be notified and another decision about the route might be made. This scenario is graphically represented in the animation you are watching now. The parking sensors and charging stations are connected to OMI nodes. OMI node contains real-time and semi-static information about each car park. This data is structured using the Mobivox semantic vocabulary. Each OMI node, in turn, is registered in IoTBNB. CoaaS uses IoT for initial discovery purposes and fetches real-time data from IMI nodes to enable the decision-making process. Now you can see a pull-based query which is issued for finding car parks in our scenario. The query defines 4 entities, namely the destination location, the target car park, the weather, and the consumer car. The destination location is defined by address. The distance function accepts several modes of transportation and as its last parameter. In this case, we used walking to specify that Claudia is going to walk from the car park to her customer's office. Other possible parameters of the distance function are cycling, driving, and public transport connection. The query defines suitable car parks by providing several other parameters, for example, the cost and availability parameters of the car park. The parking domain, despite seeming to be simple, is far from being really simple. Just look at this collection of parking signs. As a minimum requirement, the car park must have vacant spots, it should be available for a person without a special permit, the maximum length of staying should be enough, and the cost must be affordable. And the spot also must have a charging station with suitable type of the plug, power, voltage, and other parameters. The decision about the car park choice can also depend on the weather. We have defined a situation function good for walking, which you can see on the screen now. It defines the ranges of temperature, rainfall, humidity, safety of the area, and other parameters which form the good for walking situation for Claudia. These parameters can differ for each person to suit their preferences. In the query, we have specified the threshold of 0.8. In case CoaaS is more than 80% confident that it is good for walking, it can suggest a car park which is slightly further from the destination but not very expensive. At the same time, if the weather is bad or the area is not very safe in this hour of the day, CoaaS will suggest a more expensive but closer car park. This feature is facilitated by the OR operator of CDKL language. As a proof of concept, we have implemented an Android application which demonstrates how CoaaS can be used to facilitate mobility use cases. This application shows the result visualization on a map as well as the CDQL query and returned results. We also integrated CoaaS with Node-RED. We added 3 custom nodes, namely Context Query Node, CoaaS Node, and Parking Data Mapper Node. In this figure, you can see a basic flow for visualizing the parking use case. In this video, we have demonstrated the integration scenario when CoaaS is used by BMW Connected Drive system to facilitate context acquisition in bIoTope smart mobility use case. Thanks for watching!